Okay.
All right, we have two things to do today. One is to proceed with the course. The other is to decide what we're going to do about the problem session. And I'm not sure quite what to do first. I think maybe I'll proceed with the course and finish chapter 1, and then pause and look at this, and then start Fourier series. So, we were talking about a tensor product. Let me give another example of the tensor product. First of all, it occurs generically when you're dealing with composite systems. For example, two spins, or the orbital angular momentum of, say, an electron and its spin. So, in other words, the eigenstates of the hydrogen atom NLM without spin are like that. The two states of spin are this, where sigma is equal to plus or minus, which you decide. And what you have then is H on NLM is equal to En NLM L squared NLM is equal to H bar squared L plus 1 NLM. L3 or LZ NLM is H bar M and LM. Okay, so these are the eigenstates of the non-relativistic hydrogen atom without spin. On the other hand, the spin eigenstates are S squared on sigma plus or minus sigma is 3H bar. Well, let me say it in a simpler way that will get us for sure the right answer, so I don't have to do it from memory. H bar squared 1/2, 3/2 sigma, which is 3/4 H bar squared sigma, and sigma 3 on sigma is sigma H bar over 2 sigma. So these are the states that describe the spin decrease of freedom of an electron, or any spin 1/2 object. Now what you can do is you can define the direct product states, NLM sigma, which are the direct products of the states NLM with sigma. And sometimes one writes that simply as NLM sigma. And the deal is that the operators made out of S act only on the state sigma, and the operators made out that refer to the part of the hydrogen atom without spin, H, L squared, L3, and such things, act only on this state, not on sigma. So is that clear? Are there any questions?
So that's why you have 6. You have the 3 quantum numbers in LM, plus minus sigma, so you can say that you have.
Well, you have 4 quantum numbers then.
4, right.
And what did I want to say? Well, these states here are eigenstates of H, L squared, L3, and S3, and S squared. Okay? What you can do, however, is you can take linear combinations of these states and make states that you would call N, J, J3, and no, just that and J3. And these would be a linear combination of NLM sigma of these states with certain coefficients. And in fact, the coefficients would be easily written. They would be NLM sigma, NJ3. So these are numbers, complex numbers, and we would be summing them over L, M, and sigma, and these then would be eigenstates of H, so this would be NJJ3 is EN NJJ3, and if we're just thinking about a hydrogen atom, no electric field, no magnetic field, no extra stuff, then these energy levels are the same whether you have spin and whether you make eigenstates of J and J3. What I should say here is that J is the total angular momentum, and okay. So then these are eigenvalues of J squared. And also J3. But they're also eigenstates of what? Certainly S squared. Will be 3/4 H bar squared. But we're going to be summing over L and M and sigma, and so they're not really eigenstates of LZ, L3 or J, L3 or S3. And okay, so that's basically how that works. Let me ask these guys this point. Say, guys, we can move a little bit or quiet down or something. So, any questions?
Are they still eigenfunctions of S squared?
Yes. Because, somewhat trivially, because this, yeah. We're only bringing in the, this plus or minus, in other words, spin up or spin down. But we'd be summing over the M, and actually, I think, I'm trying to remember whether one can also arrange with the eigenstates of L squared.
I thought the reason we introduced J was because L and S are no longer vectors. They're no longer commute with Hamilton. They're no longer conceptual. I thought that's why you introduced J.
Well, let's put it this way, this basis is the right basis to use when the Hamiltonian doesn't commute with LZ or it would just be LZ typically. It would normally commute with L squared. Or if it doesn't commute with L squared. Because if it doesn't commute with L squared, it's very possibly not going to commute with J. But if this is the ordinary Hamiltonian with just a central potential due to a fixed proton, then you have H would commute with J, and of course J squared commutes with J3. The idea here is that J squared is a scalar under rotations. And what I'm trying to remember is whether L squared is still, so it was L squared, let's see, L squared with
As long as you know.
J squared. J squared is L squared plus 2 L dot S plus S squared. Well, this commutes with that. Yeah, I think one also has, we can also arrange for this to be just a sum over M and S, and then we also have, so then L is another quantum number here. And for that matter, S squared is somewhat trivial, so this is H bar squared L plus 1, N, J, L, J3. And of course, they're all eigenstates of S squared, as I said. Okay, so these are two standards. So this is an example of the direct product. Okay, well, let me go on then to finish this. We talked about density matrices already. One thing that I may not have mentioned last time is that since the density operator is Hermitian, it follows that the density operator has eigenstates that are complete and orthonormal. The eigenvalues are real. In fact, because the density operator though is non-negative, the eigenvalues are non-negative. So rho k is written equals 0. The trace of rho is 1, is the sum of these rho k's. K we say 1 to n. The density operator itself then has the expansion sum on k from 1 to n. And I'll call the state k prime rho sub k prime. The reason I'm using k prime is that in the notes I use n for just an arbitrary basis. So in other words, you can diagonalize the density operator. The density operator is diagonal in the basis provided by its eigenstates. And rho k then is the probability that the system is in state k. So that's what rho k is. All right, now there's two cute things we can do with density operators. If f and g are two states, we write the inner product of these two states as f rho g. Now this is not the usual inner product, but it is nonetheless satisfies the axioms of an inner product. But this is a non-Hermitian inner product. I'm referring to that section on the inner product way back there where we use those terms. Looks like term Hermitian. Yeah, that's right. This one is, you can say it's non-Hermitian, you can also say it's semi-definite. So it's semi-definite inner product. or a degenerate inner product. Well, let me stick with this one for the moment. The reason why this is non-degenerate is that suppose we consider the norm of a vector itself. Well, that's just going to be f rho f. Well, if rho describes a system that has zero probability of being in the state f, then this would equal 0. But the state f has norm 1, so it's not the 0 state. But it's very possible for rho to describe a density operator for a system that has no chance of being the state f. And for example, if we had 3 states, 1, 2, and 3, all orthonormal, then the density operator rho might be a half 1, 1 plus a half 2, 2 would be a state such that 3 rho 3 would be identically 0. Okay. Let's see, are we turning that thing sometimes?
Oh, sorry. Completely blinking out on that.
So in other words, this is an example of a case where 3 is the unit vector, and yet the inner product of 3 with itself, defined here as this, would be 0. So that's why it's not. That's why it doesn't satisfy the conditions for a Hermitian or non-degenerate inner product. Now, nonetheless, it still satisfies the Schwarz inequality. And the Schwarz inequality would be FF PG, that's a G, is greater than or equal to the inner product of F with G squared. So for density operators, this would be, for this inner product, this would be F rho F G rho G greater than or equal to the absolute value of F rho G squared. And so this is something that's, in fact, what we've essentially derived here through the Schwarz inequality is a result that's true now for any 2 states, F and G, and any density matrix rho, or any density operator rho. This is a perfectly general result. Another degenerate inner product now applied to operators. So here we were talking about states, now we're talking about operators. This can be written as trace rho A dagger B. We can show that this satisfies the axioms for an inner product, but of course it's always possible that you could have A being trace rho A dagger A, and this could be 0 if it turned out that rho, say, was the outer product of a vector that the operator A mapped to 0. So A dagger A has non-negative eigenvalues, but it could have a 0 eigenvalue. Well, if rho is the outer product of the vectors, maybe I'm talking too quickly. Suppose, in other words, A on, what do I call it? M equals 0. Then let rho be the outer product of M with M. Then this inner product of the operator A with itself would be the trace of MM A dagger A, and this would simply be the diagonal matrix element of A dagger A in the state M, and since AM is 0, this would be 0. So that's an example. That shows then that whereas A is by no means the zero operator, all you need for this to happen is for A to have one eigenvalue that's 0. Or not an eigenvalue that's 0. I spoke incorrectly. A just has to map one vector into 0, which I guess does mean it has an eigenvalue of 0. But A dagger A has an eigenvalue that's 0, the same thing. Okay. All right. Anyway, that's another inner product, and we then, applying the Schwarz inequality, we get the following result: trace rho A dagger A, trace rho B dagger B is greater or equal to the absolute value of the trace of rho A dagger B, absolute value squared. So this is simply, in other words, AA BB greater or equal to the absolute value of AB squared, with AB defined as this. So that's an example. I think just because of the reasons of, well, maybe I will mention these things. Do you want me to talk about the quantum optics application of some of these things? Yeah? Okay. Well, all right, let me take a drink of tea. The basic theory behind the interaction of light with matter is quantum light dynamics, and in that you have the electric field operator EI at X is EI positive frequency part at X plus negative frequency part. This one basically are the ones that annihilate photons. So they have things like A sub K, and this one, these create photons. So they have things like E dagger K. And Glauber defined the first order correlation function Bij1 at points X and Y as the trace of the density operator times E minus I at X, Ej positive frequency Y, close parentheses. So the trace of those two, which you can think of as the inner product of, in fact, since E minus I of X is actually E plus I of X adjoint. So this can be thought of as E plus I of X inner product with E plus J of Y. So this is, and this correlation function is one of these degenerate inner products. And so this relation here tells you that GII1 of XX times the first order correlation of JJYY is greater than or equal to G1 IJ XY squared. Okay, so that's a general inequality following Schwarz, follows from the Schwarz inequality. It is the Schwarz inequality. And if you apply this to interference fringes, then you get the sharpest fringes when you have equality here. So if you have equality, this guy is as big as possible, and this is the guy that causes the interference. You get sharp fringes there. And in fact, this occurs when the density operator rho is an outer product of what are called coherent states, which are sort of an idealized laser. It's more general than a laser, but it's idealized. In this case, these states are eigenstates of this field, this positive frequency part, with eigenvalues that are that can be obtained by taking the positive frequency part of the electric field operator and replacing all the annihilation operators with alphas. And that's because A sub k on alpha k is equal to alpha k for all the modes k, normally an infinite number of modes. All right, that's the end of that chapter. I'm sure there are other things along in there, but I'll stop here. Now, big question. What are there any questions? Is that a question, or are you just stretching?
No, it is a question. So I know that for pulse laser systems, you use some sort of autocorrelator to find the temporal pulse.
What?
So your pulse laser system goes, let's say, 500 femtoseconds, and you shoot the laser into something called like an autocorrelator to find exactly how long is my pulse width. Is it 500 femtoseconds, 550 femtoseconds, etc. Is there any, pun intended, is there any correlation between this and that little box?
I'm sure there is, but although I did my thesis under Roy Glauder's supervision, I left the field because I thought basically he had answered all possible questions in the field and it was stupid to continue. So, and I'm a theorist, not an experimentalist. Okay. So that's the sort of question you can ask Wolfgang Rudolph, or Sheikh Bahai, or Jean-Claude Diels, or...
Because everybody I ask, I say, how does this box work? And they say, it just works.
Yeah, well, if Jean-Claude doesn't know, I don't know. Let's say that. All right. I'm not going to do the chapter on group theory now, but at least I'll define what a group is, just so everybody hears what a group is. So, what is a group? A group is a set of objects, F, G, H, etc., and an operation called multiplication. And there are the following properties. If F is in the group, G in the group, then FG is in the group. Secondly, for elements in the group, F times GH is the same thing as FG times H. This is called closure. The product of two elements is in the group. And it doesn't matter whether you multiply. If you have the product of three elements, it doesn't matter if you multiply the second two first or the first two first. It's called associativity. The third thing is that there's an identity element E in G, such that EF equals FE equals F. So it's an identity element. And 4 is that for every element in the group is an inverse. F inverse F equals F inverse equals the element. Now, the reason why groups are important in physics is that if you have any transformation, physical transformation, for example, translation in space, translation in time, rotation in space, parity transformation, reflection in space, charge conjugation, you flip the charges, time reversal, well, that is so spooky. Anyway, you have any of these transformations, they naturally form a group because the product, suppose you have translations in space, or Lorentz transformations also. So you have some sort of a transformation G, you follow it by a transformation F, well that's another transformation. Obviously you translate an X and then an Y, you go both X and Y, and that's the same thing as an XY translation. Similarly, the associativity happens just automatically. The identity is the transformation that doesn't do anything, and if you do a transformation, you can invert it, so that's the inverse. So, in other words, the transformations of physics are naturally represented by groups, and in fact, they're typically represented by unitary groups, linear unitary operators. The exception, the spooky case, when time reversal is involved, and then you have to represent them by anti-linear, anti-unitary operators. And I get shaky knees. So much for the group theory chapter. Now, we're going to start Fourier series. Oh, I forgot to pass these around. I brought them here. Okay, now, Fourier series, from a certain point of view, Fourier series is like linear algebra. You can think of it as an example of linear algebra, but with two differences. One is that we're talking about functions, which of course, functions can be thought of as vectors. But the point is that we're going to be thinking of an infinite dimensional vector space. So we're going to think of an infinite space of functions. And in particular, the basis set of functions, one interesting and useful basis set of functions are just complex exponentials, e to the I nx over the square root of 2 pi. These are functions that are orthonormal on the interval, say, 0 to 2 pi, or 0 to 2 pi for definiteness. So En, or if you want in Dirac notation, En is equal to, hold on, before we continue with this, let me discuss this issue of what to do about the problem section. So let's see. Here are the possible. Why don't I go over and use this board here? The possible times for the problem session are Tuesdays, room 190, 11 a.m. to 2 p.m., and 3 to 5. 5, room 5, 2 p.m. to 5, and 184, 120 to 5:30. I'm kind of amazed that these things are so available. Thursday, 190 is available from 12 o'clock to 2, and 184 is available from 1:20 to 3:30. All right, or before 11. But I don't want to get you guys out of bed that early. Okay, so what do you think of as reasonable times?
4 Tuesday?
Well, that's fine. All right, let me write that down. So 3 to 4 Tuesday. We could also do 2:30 to 3:30. Of course, these are supposed to be 50 minutes on Thursday. $184 is sort of the ideal room if enough people come. Otherwise, room 5 is just as good. Okay, so come on, give me some guidance.
What about one? I want either of those days. Or,
Well,
I don't know, this one.
1 to 2.
Yeah. Something like that.
On
Either day.
yeah, the trouble is, Mom lectures from 1 to 2. I don't know. I don't have to go to that. But I sometimes do. You have class when?
2 to 5 on both those days.
2 to 5 on Tuesday, Thursday.
Would noon to 1 work instead of 1 to 2?
Why would that be better?
Well, because that doesn't conflict with the Gilman lecture, does it?
He still has a 12:30.
Oh, okay. Sorry, I misheard you.
1 to 2 would put us in 190. Which is, 190 is a room with cushy chairs, but it'd be crowded if 10 people came. Well, it's not crowded to sit, but there's not that much blackboard space. But are you thinking of coming actually?
Not every time. But I always.
Is there anybody who has a problem with 1 to 2?
You can go earlier, so 11 to 12. I mean, anytime.
All right, why don't we say then 1 to 2 and 190 on Thursdays? That way we can, instead of having one tonight, we'll have it tomorrow, 1 to 2. Okay, is that all right? Okay, so let me write this down. Do you have a pencil or something? 1 to 2, 190 Thursday, right? And it'll really be 1 to 150. Okay. Yes?
Could you make it 1:30 to 2:30? Never mind.
Yeah.
Because I have a problem session from 12:30 to 1:30.
Is that all right with you?
That's fine.
Okay, so in other words, we're doing in this section this. Oh wait, did you say to 2:30? What did you say?
2:20. 1:30 to 2:30.
So that'd be down in 184.
Oh. Okay, 1:30 to 3:20. No, 1:30 to 2:20. Fine. Okay, so let me change it then. All right, so let me write this down again. 1:30 to 2:20, 184 Thursday, right? Okay. All right. And 190 by, oh, no, it's 184 we decided, right? Yeah. Yes, okay. So that gives us this room. Good. All right, now let's get back to this business then. What we've got is all the normal functions, and you may say, why did he start Fourier series with complex exponentials? Well, because it's easier. The complex exponentials are easy. The real exponential sine and cosine functions are hard because they're not so symmetrical. This is the inner product. It's the integral 0 to 2 pi en star of x em of x dx. And in particular, that's integral 0 to 2 pi e to the inx over root 2 pi complex conjugate e to the imx over root 2 pi dx, which is an integral 0 to 2 pi e to the I m minus n x dx over 2 pi. Okay? Yes.
Why don't we need an n somewhere in the coefficient to normalize?
Why don't we what?
Why don't we need an n somewhere in the coefficient to normalize these?
Well, you're going to see why not in a moment when I do the integral.
Okay.
This is what you use to normalize them. All right.
So
I see.
when you say the orthonormal, are you saying that orthonormal?
When I finish the equation, that'll tell us what's orthonormal. All right. Now, to do this integral, suppose m is equal to n. Then this is e to the 0. Anything to the 0 is 1, right? So this is 1 over 2 pi integrated from 0 to 2 pi. That gives us 1. Okay. So this is Kronecker delta. In other words, it's delta and m, at least for n equals m. Now what if m is not equal to n? Well, then you have to actually do the integral with your fingers. And then what you get is you get e to the I m minus n x divided by I m minus n, so that's the indefinite integral, divided by 2 pi, evaluated at 0 and 2 pi. But you put x equals to 2 pi here, and you get e to the I some integer times 2 pi. But e to any integer 2 pi is 1. And then you put x equals 0, and you have e to the 0, and that's 1. So this is equal to 1 minus 1 over I m minus n 2 pi, which is 0. This doesn't work if m equals n, because then you've got 1 minus 1 over 0, and then that's undefined. But the case m equals n is the simplest case. It's just 1 over 2 pi integrated 0 to 2 pi. Okay, so this is the rule. This is what's meant by there being orthonormal. Any other questions? All right. So what this means, of course, is this Kronecker delta. 1 if n equals m. 0 if n is not equal to m. Okay? All right, so now we have this very nice set of orthonormal functions, which we can think of as orthonormal vectors. And so we want to see how big a space it spans. Well, it spans whatever it spans, because, in other words, we can write a function f of x as some sum n equals minus infinity plus infinity c sub n, e sub n of x, or equivalently the sum n equals minus infinity to infinity c sub n e to the I n x over square root 2 pi. Okay. So this is an expansion. For any set of complex numbers Cn, this gives us some function. Now, if the functions Cn are all big, then it's possible that this series doesn't converge. Okay? That as you sum out from minus infinity to plus infinity, these things, the thing just goes all over the map, in which case that's not a good representation. But and in fact, let me just tell you what the kind of nice sort of sums are. If this sum from n equals minus infinity to plus infinity, absolute value of Cn squared is less than infinity, if that converges, then this is a nice function typically. So let's just sort of rule it. All right, now let's find out what the relationship is between the function and the coefficients. All right. Well, to do that, we take the inner product of En with f, and, or let us say instead of En, I'll just take it as Ek. Well, this is a sum. This is the inner product, Cn, the inner product of Ek with En. And that inner product is simply sum Cn delta Kn. So that is just Ck. So in other words, Ck is just the inner product Ek with f, which is to say the integral 0 to 2 pi e to the minus I n x over root 2 pi f of x dx. So that's what Ck is. It's been an awful long time to do that in notes here. I guess I should. For sure those rounds. I hope you're right. Okay, any questions? Okay, so these are the let's see, I'm sort of, what I'm doing on the board is slightly slicker than what's in the notes here. Okay, well, what kind of functions can we represent this way? I said, for one thing, you get nice functions if these coefficients aren't too big as n goes to infinity. But there's something else about them that's immediately apparent, namely they're periodic. That is to say, f of x is equal to f of x plus 2 pi. Or equivalently, f of x minus 2 pi. And the reason for that is that f of x plus or minus 2 pi is this sum n equals minus infinity to plus infinity Cn e to the I n x plus or minus 2 pi over the square root of 2 pi. But this is just equal to sum n equals minus infinity to plus infinity c sub n e to the I n x over root 2 pi times e to the plus or minus I n 2 pi. But n is an integer, and so this thing here is all equal to 1. So this is just the sum n equals minus infinity plus infinity c sub n e to the I n x over root 2 pi. Okay? So So when you express a function as a linear combination of these EDI and X's, these orthonormal functions, or orthonormal vectors if you want, you always get a function that's periodic of period 2 pi. All right, let me get a sip of tea. All right, now, so we have a formula for the CKs, namely like that. Oops, all right, somebody should have told me on this. I use an N here because we've been using N so much. This is supposed to be a K. This is EK. So this is EK of X star. All right, now that we have a formula for the CKs, let's write f of x as a sum. Now, for some reason, I'm still using the n. Okay, now, on the other hand, that's a sum, n equals minus infinity to plus infinity, EDI n x over square root of 2 pi times Cn. But Cn is the integral from 0 to 2 pi e to the minus I n y dy f of y over square root of 2 pi. So this is all together. Let me interchange integration. This will be an integral of sum n equals minus infinity plus infinity e to the I n x minus y over 2 pi f of y dy. And this thing is equal to, of course, f of x. Okay, now I want you to look at that for a minute, because what this says is f of x is here. We've got something involving x and y here, and there's this integral of f of y dy. Okay. Dirac introduced a notation to this. It's called his delta function. So in other words, any expression, the delta function is such that you integrate f of y dy, and what you get, if you have delta of x minus y, what you get is f of x. So that means that the Dirac delta function I'm sort of out of space here, should be represented as the sum n equals minus infinity plus infinity of e to the I n x minus y over 2 pi. So that's an expression for the delta function. Another way of writing that is saying the delta of x minus y is equal to a sum n equals minus infinity to plus infinity en star of x en of y, which of course is the same thing. In other words, the sum n equals minus infinity to infinity e to the minus I n x e to the I n y over 2 pi. But you can also write this as the inner product of x with y in the sense of x identity operator y, and this is then x sum en y and e to the minus infinity plus infinity. So in other words, the identity operator is the sum of the outer product of the vectors representing all of these orthonormal functions. Okay. So now, are there any questions?
I'm sure this is a notation question, but we define the coefficient Cn in terms of the function f of x.
Yeah.
And then it seems like all of a sudden we're defining them in terms of some function f of y.
Oh, well, I mean, that's fine. Y is a dummy variable.
Okay, both dummy variables, there is no correlation. Okay.
Yeah, the function f of x is just the function f evaluated at x, f of y is the function f evaluated at y.
Fair. Okay.
All right. Well, what we can also do is we can write this in terms of, we express these, you know, e to the I n x is of course cosine nx plus I sine nx. And consequently, we can write delta x minus y as 1 over 2 pi sum cosine n x minus y plus I sine n x minus y. On the other hand, sine of n, sine is an odd function, so you have the, you know, if n is 32, you would also have minus 32, and they're going to cancel. So they go away, and you just have 1 over 2 pi sum n equals minus infinity plus infinity cosine of n x minus y. And equivalently, that's, now the cosine is even. So this is in fact, the first term is n equals 0, that's just 1. Cosine of 0 is 1. So this is 1 over 2 pi plus 1 over pi sum cosine n x minus y, n equals 1 to infinity. So I've absorbed the cosine minus n case is just, I've just doubled, I've just used the factor of 2 and got rid of the 2 in 1 over 2 pi. Okay? Now, do I think this is particularly important? No. But you might need it at some point. Okay. Now, we've been considering the function f, but of course it's natural to think about the function f star. Well, f star of x is going to just be the complex conjugate of the series for f. So it's going to be e to the minus I nx over root 2 pi. Okay. On the other hand, we can rewrite that as a sum n equals minus infinity plus infinity c minus n star e to the I nx over root 2 pi. In other words, we can just sum over minus n instead of n. And that tells us then that the coefficient Cn of f star is equal to c star minus n of f. So the coefficients of the complex conjugate function are the complex conjugate of the negative, of the coefficient of, in other words, Oh, I don't know. I just have to repeat it. Cn of f star is C minus n star of f. Of f means the coefficients used to represent the function f star are the complex conjugates of the inverted coefficients of the function f. Used to represent the function. If the function is real, though, this is equal to Cn of f. If f is equal to f star. That means then that for a real function, Cn is equal to C minus n star. So this is a condition for real functions. On the other hand, for imaginary functions, f star is going to be minus f, and so what we have is Cn is equal to minus C minus n star for imaginary functions, because f is equal to minus f star, and Cn for minus f is minus Cn. Anyway. All right, any questions? Now we've been using the interval 0 to 2 pi. In fact, we could have taken an interval minus pi to pi. Or we could have gone from, we could have chosen an interval 1/2 to 2 pi plus a half. You can use any interval you want as long as it's a length 2 pi. And whatever interval you use, so say it goes from r to r plus 2 pi. And in that particular interval, the function will do whatever it'll do. But, and the function may or may not, the function you start with may or may not be periodic. But the function you represent, that is to say the Fourier series, intrinsically is periodic, a period 2 pi on this interval. So this thing will then do the following. It'll go, so it'll look like this. I should give you a simpler example. Suppose we're representing the function f of x equals x. Suppose that's the original function. Then you might write that as a power series, as a Fourier series, Cn eInx over root 2 pi. Well, f of x equal to x is certainly not a periodic function. So what we would get, if we represented it here in this way, and suppose we use the interval 0 to 2 pi, then what we would get, 0 to, say, 2 pi, we would get, well, I can't go up that high. It would look like that. But then, over here, it would start again and do that. And then it's a 4 pi. And then it would do this again. So that's what the series would look like. And if you truncated the series at some value, say you've summed not from minus infinity to plus infinity, but from minus 1,000 to plus 1,000, then what you'd be getting is you'd be getting jagged effects at here and here. And that's because the function gets really nervous over here. It knows it's supposed to be 1, but it's also supposed to be 0. And so the function is schizophrenic, and that's called the Gibbs overshoot. Did I tell you about Gibbs? Gibbs, of course, he was probably the first great American scientist. Maybe I'm being, maybe I'm just showing that I don't know enough history, but I think he was the first really great American scientist. And he was at Yale, and he was studying statistical mechanics and thermodynamics. And did I tell you about it? Did I tell you something? People at Yale didn't appreciate or understand what he was doing. And at times they didn't even pay him a salary. But he went on and taught nonetheless and wrote articles. And he became famous. Well, the people throughout the world who were on the top of the field of statistical mechanics and thermodynamics, chemical physics and so forth, such as Nernst in Germany, appreciated what Gibbs was doing. And in fact, Nernst came to Yale after Gibbs had died. And Nernst was a famous German professor, and this was, I guess, 1880 or so. And so many of the professors from the physics and chemistry departments at Yale went to the train station and waited and bowed and scraped before Nernst as he got off the train. And Nernst said, and then they said, well, we'll take you to Maury's for lunch. How about that? And Nernst said, but first I want you to take me to the monument to J. Willard Gibbs. And the professors looked at each other and said, with great embarrassment, because they had erected no monument to J. Willard Gibbs, and in fact they hadn't even paid him for part of his teaching there. And the story then gets a little bit frayed, the version I've heard. It's not clear. One version of the story is Nernst was so pissed that he got on the train, went back to New York, or got back on the train and went back to Boston, or maybe even went all the way back to Germany. Eventually, so he did. But the other version is that he stayed in New Haven long enough to put a plaque on the wall at Yale in honor of Gibbs. It turns out, by the way, that Gibbs's father was a lawyer, and he was the lawyer who defended the Africans who revolted on the slave ship Amistad or something? Amistad, which was made into a movie. And he got them off. They were all accused of murder, but he was such a good lawyer that he got them all declared innocent. Okay, so, well, class is almost over. Let me just treat something silly here. We've got, I chose to put the square root of 2 pi's where I did because I wanted these functions en of x to be orthonormal. Well, sometimes you get tired of having so many square roots of 2 pi's. And so some people instead give up the orthonormality, or the normality, I should say, of these basis functions, and instead we can define coefficients dn equals cn over square root of 2 pi. In that case, f of x is represented by a sum dn dnx from minus infinity to plus infinity. But then, because we've divided by square root of 2 pi, this is an integral, say, 0 to 2 pi dx now over 2 pi e to the minus I n x of x. Okay? So sometimes to only have to write 2 pi's once rather than twice, and to get away from the square roots, you can do that. And now, if you're in a tight situation on a test, for example, and you don't want to waste a lot of time thinking about where to put the 2 pi's, then do it the way I did it, where everything has the 1 over root 2 pi, and then the thing is symmetrical and you won't get into trouble. Whatever you do, don't mix that convention with this one, because if you put the 1 over square root of 2 pi's in one place and the 2 pi's or unity in the other place, then, of course, you've got the thing wrong. Okay, well, I think we'll just start then next Monday with an example. Can I use your? And we'll meet tomorrow. And so we'll meet tomorrow. Let's just review when this is. 1:30 in this room tomorrow. We'll do a problem session. And I think it would be a good idea if at least some of the people came with laptops, because I think maybe the thing to do is to fool around with Maple or Mathematica or MATLAB and maybe do a singular value decomposition or two, just to make sure that everybody can do it that way. All right. And if nobody comes with a suitable laptop, we'll all go to my office, and I have 2 or 3 of those programs on my office.